Hey, good morning, everyone. I hope that you had a good weekend and also doing well with social distancing. So, if you remember last time we talked about a memory hierarchy, the trade-off between highly expensive, very limited space of memory elements versus the speed, right? And then because of that, we do the one of the primitives that people try to use is trying to cache those information that are expected to be um, presenting itself or to be accessed in the near future, right? So we talk about the concept of swapping a process in and out, which then lead to fragmentation. And then we talk about the different techniques to solve that. And one of the very important concept in memory management was paging, right? So we talked a little bit about paging before in the previous class, and today we will recall that a little bit, right? And then we would go to virtual memory, the nice concept of virtual memory, and then go into page replacement policies and different ways to replace pages. I will hand it over to Dave, who was instructor in Silboda before, and he had an excellent set of lectures that are recorded. So please enjoy the video, and also reach out to me and also on post on class discussion if there's any questions or any point that you want to discuss. Um, I will set up a Zoom link so that we can have a conference call if you have specific question. All right, enjoy the lecture, and I will see you in the next class.
Welcome back to the University of Colorado at Boulder. We've been talking about memory management, and we're going to talk some more today about paging. You remember that fragmentation is the splitting up of the memory. So in this case, we have our RAM, we have processes and the OS in there, and then we have these unallocated blocks. And if we had a new process come along that was bigger than any one of those blocks, we couldn't put it into memory because it is non-contiguous. And we have been allocating processes as a contiguous area of memory. We could rearrange all these things to get rid of this fragmentation, which is called external fragmentation, but we don't want to have to move data when we don't need to. So we could actually do defragmentation. That would be collecting all that unallocated space together by moving the processes that are there. We talked a little bit about how we could get rid of some of this fragmentation if we were to segment a process. And segment was we could create different units within the process. And then we could look for smaller memory blocks. Using these smaller memory blocks, we could then place a process into memory by just finding any number of unallocated blocks to fit the blocks we needed. And only if we couldn't find one big enough to hold our blocks from the segments from the memory, from the process memory, then we would need to swap a process out at that time. Well, we can take that one step further, and we can do paging. So in order to get rid of external fragmentation, we're going to take the logical address space and just break it up into fixed size pieces. So instead of breaking it up into individual segments, each segment might be an unknown size, we're going to just take it and break it into fixed size pages. So in this case, we broke it up into 5 different pages. We can also do that same thing with main memory. So we can take main memory and break it up. So when we break up the logical address space, each one of those is going to be a page. When we take main memory and break it up into fixed size units, those units are going to be called frames. Now, the size, the fixed size that we are using, can be the same between the two, or it could be different. we could make the frame, say, 4 KB and make the pages 1 KB, in which case there would be 4 pages in each frame of main memory. But for this course, we will just always talk about the page size and the frame size as being the same, just to make things a little bit simpler to talk about. There's nothing hard about implementing the other way. It's just a little bit more complex. It takes a little bit more effort to do it, and we really don't need it when we're talking about the functionality. So each page of logical address space, we can place it in any frame. So we could go and say those 5 pages we had will go into 5 frames, but we can pick any frame for it to go in. In this case, we have page 4 before we had page 0, then page 2 and page 1, and none of it is contiguous. We're able to now just map those pages from one space to another. And the way we're going to do this is to have the memory management unit take care of this for us. We're going to do it by having a page table. And the page table is just a logical to physical translation. So we're going to keep for each logical page that we have in the logical address space, we're going to keep which physical frame did we actually put that page into. So as you can see here, we can then just have the MMU, whenever we go to access something in logical page 0, will automatically point us to that physical frame. And then likewise, if we went to get 1, it would point us to frame 4, and page 2 would take us to frame 3, etc., etc. The nice thing about this is we had 3 unallocated frames, and those could actually be allocated to some other process. They're not contiguous, but now we don't care. So if we had a process that needed 3 or more, we could take those 3 and allocate it. If we run out of space, we don't have enough to put it in, then we'll have to pick a process to remove it. When we remove it, those pages would then become available, and we could pick between those pages to find enough to load the new process. The great thing about paging is the user's view of memory is still a contiguous block of space. So we're looking at a logical address space, and it just goes from 0 to max. We don't have to figure out exactly where that is or how to break it up. We can just say that it is one big logical space. Typically, we break things into 4 to 8K blocks. For example, if we were breaking it up, a 32-bit address can access up to 4 gigabytes. And if we were doing 4 KB per page, then we'd end up with over 1 million entries in that page table for every single address. And if we stored every single possible page, then our page table, it would need at least 20 bits per entry, so we'd end up with about 3 megabytes per process. Now that's not too much in modern days, but if we had, say, 1,000 processes, all of a sudden now we're using up quite a bit of memory just to hold those page tables. So what are the address limitations of doing this? Well, in a normal 32-bit machine, we can access up to 4 gigabytes of memory, and we saw how big the page table would be there. If we were to extend this a little bit, we could actually have 32-bit table entries, and then if each one of those was accessing 12 bits, 4K, then we would be able to access essentially 16 terabytes of data, of memory, even though an individual process could only access 4 gigabytes. And if we looked at a 64-bit machine, the address space is now up to 16 exabytes, which in modern times, that's more memory than you can get on a single machine. There's also support for very, very huge or very, very large frames. So we could end up with each frame being 4 megabytes. And that way we don't have to store a whole bunch of bits to look up where that data is in real memory. So our page tables would be smaller, but we'd end up with very, very large frames. Is that a problem? Well, we have no more external fragmentation, which is great. So every single possible byte of main memory can be used, but we do have some internal fragmentation. So what is internal fragmentation? Well, suppose we have a process that's 4,100 bytes long, and each page is 4 KB, so that'd be 4096. So in order to store this, we would have to allocate not just one frame plus 4 bytes, we'd have to actually do 2 pages. So we'd have to have 8K. And so it would look something like this. We'd have page 0, and then we have page 1, and we would be using all of page 0, but we're only going to be using 4 bytes of page 1. That means we have 4,092 bytes that we're actually wasting. Now think about this. If this was a 64K or 128K frame, or say 4 megabytes, and what if I had a 4 megabyte plus 1 byte process? I'd have to allocate 8 megabytes, and I'd have a lot of extra internal wasted space. So we do get some internal fragmentation with this. So the smaller our frame size and page size, then the less we end up wasting to internal fragmentation. In paging, we also have to maintain a pool of which of the physical frames are actually free. So when we are not using a frame for any process, we need to be able to map all of those into a free pool so that when we need new frames, we can just go to that pool and allocate one. In fact, we can allocate any of them. It does not matter anymore. We can have it just added into the page table and everything works. When we're using paging, we have to take the logical address now and divide it into 2 parts. We're going to have the logical page that address is accessing, and then we're going to have the offset within that page. And if we make it a power of 2, then we are just allocating a number of bits for the logical address and a number of bits for the offset. So most of the time we always lay this out as the logical page is always the most significant bits of the address. And then that's the same as taking that whole virtual address and dividing by the page size. So essentially we're just shifting it down and using those bits. We use the logical page then as an index into the page table to retrieve the correct physical frame. And so now we can take and use the physical frame along with that page offset that we had, and that's going to give us our physical address. And it's the MMU that is responsible for translating from the logical address into that physical address. So this is what it kind of looks like. CPU has a logical address it wants to access. The MMU is going to split it up into the 2 pieces. It's going to take the upper bits and it's going to look up in the page table to find that frame number. It's going to then grab that frame number and combine it with the bits, the lower bits from the logical address, and then go off and access RAM. So given that, how are we going to implement this? Well, we could do it as a set of hardware registers or memory. So we can have it all in very fast memory that's all in hardware within the CPU itself, within the MMU. That would allow us to have very fast translations, but every time we do a context switch, we'd have to unload that page table, load in the new page table to then start up the CPU with that new one. And that can take a lot of time depending on how big that page table is. So we'd have a slow context switch time. The other thing is if we had to have 1 million entries, it's just going to be too expensive to be able to handle this as hardware. So we need to come up with another way. Second option is to use a page table register. So if we store the page tables in main memory, then all we really need to know is for that process, for each individual process, where is the page table? And then if we have a pointer, then we can just have the MMU grab that information, jump into the page tables, get the physical address out. This can handle any size page tables because all we are doing is just accessing memory. We have a fast context switch because all we need to do when we have a new process come in is just change that page table register, and then we can look up every single frame. But we're going to be slow because each instruction is going to require 2 steps. One, finding the actual physical frame, and then going and accessing that physical frame. So we have to access memory twice. Once to get the frame from the page tables, and the second one to get the actual data. So it would look something like this. CPU has a logical address it wants to get, so the MMU goes out and finds the beginning of the page table, jumps down to wherever that data would be, grabs those values out of main memory, puts it into the physical address along with the lower bits of the offset, and then uses that to go get the data, and then that data is returned to the CPU. So again, we've accessed memory twice, and if memory accesses are slow, we're going to run into problems. So there's a third option. What we should do is just cache a subset of the page table, the things that we're going to be using all the time. And we do this through the translation look-aside buffers. So this is a fast solution to the slow 2-step. We try to eliminate doing that 2-step by remembering the pages that we've been accessing recently. There's different ways that we can do this. We can do it as the most frequently referenced, or we can use the most recently referenced. Different ways that we could do the caching. And this is what it would look like. So the CPU has a logical address, and what it wants to do is go and look up in the TLB. Now the nice thing about this, you can see that there's a single line coming out of the logical address and then in multiple arrows. This is doing associative memory, which means we are looking up all of the data in the TLB at the same time. So we don't have to do it as a linear list of checking each one. We can do them all. And if any one of them hit, meaning that we had the logical page number in there, then we'll have a TLB hit, and we can just take the frame out of the physical frames. Now, if we miss, then we're going to go ahead and go to that pointer, the page table pointer, and we're going to go into main memory and grab that information for which frame it was. But instead of just putting it into the physical address, we're also going to remember that we just accessed that. So we're going to put the data back into the TLB. Now that we have the physical address, we can go get the target information, get that actual real bytes, and return that information to the CPU. So on a context switch, we still have a problem now because the TLB entries need to be invalidated or taken out because they were only for the process that was running. So there's different ways that we could do this. We have ways of being able to process this in the x86, but there's alternatives to doing this. We could also in the TLB include a process ID, so each individual process would have its own ID. We could add the ID along with the logical address and the logical page to look those up in the TLB. just means that we have more cost because we have more bits that we are storing and want to do this all simultaneously. So the additional hardware costs come along. But the nice thing is we don't have to swap things in and out on each context switch. We can let things naturally progress. And then if we're switching back and forth between processes, we could have all the information in there. And there are different CPUs that use these different mechanisms. There's also a problem here that we could take care of is if we have something that's frequently used, a page that's frequently used, we can actually keep it from being invalidated. So that means that we could keep things that we know that we're going to access next time this process runs. And there are different processors that take advantage of having that hardware. We could also flush out just individual entries. So we could have a whole bunch of data there and then only flush out the things that we needed to take out for an individual process that was running. So let's talk about paging and caching. So the MMU really needs to interact with the L1 and L2 data. And how is it going to do that? It really depends on whether we are trying to cache things as virtual or physical addresses. So think about this. If we store the information by the virtual address, then we could look it up. But that wouldn't give us any information about where it was in memory. We'd still have to do those things. So it may be that we want to look up things both ways. If we're using the physical, we're going to have to convert from virtual to physical before we can actually even look at the cache. But there's times where we'd just like to know, hey, I've been accessing this same information, this same virtual address. So it'd be really nice to be able to have both of these mechanisms. So this is how it's going to work. We're going to have a logical address, and then we're going to go and try to access our L1 or L2 caches. And we're going to use that logical address to look in that first cache. And if we have a hit, then we'll just give the information back to the CPU. If our virtual address isn't in the cache, then we have a miss, and we're going to go through the normal TLB search. So simultaneously, we will look up in all the pages to find which one actually matches and get that frame number out. So we have a hit in this search. If we have a miss in the search, then we have to go through the two-stage method. We have to go to the physical page tables, grab the frame out, put it into the physical address, put it back into the TLB. Now that we have that physical address, we can look up in a physically indexed L1 or L2 cache. And then if we have a hit, we'll end up giving the information back to the CPU. And if we have a miss, then we'll go to that actually target memory, grab the information out, and send it to the CPU. So here we have both a virtually indexed and a physically indexed cache that we are using. So using this introduces some problems. There's something called the hominy problem, in which two processes use exactly the same virtual addresses as the previous ones, as the previous process. And therefore, we could have hits on that cache. So there's got to be ways to adjust the virtual addresses so that we don't return that wrong information. And there's a couple ways we could do it. We could flush the cache on each context switch. That means we take everything out of the cache and we have to rebuild that cache when we do a process switch. We could also just add a space ID, a process ID, that says, here is the process ID to go along with those addresses. And so we would then know that this new process with the new ID with the same address would actually be two different entries. Now, that's great, except it requires more hardware support and extra bits and extra comparisons. So it really adds in a whole bunch of extra things to go on, and our caches are already small. This would make them even smaller on the amount of data that they could hold. We could also do something to where we have virtual address spaces that don't overlap. So process 1 would use 0 to max. Process 2 would use max plus 1 to some larger number. But this violates that process to where we are creating the processes to where we independently own an address space. And so we really probably wouldn't want to do that one. So in practice, most L1 caches are virtually indexed because they are small and fast, which means we come up with the virtual address, which is right in the code. We can immediately look that up very fast in the L1 cache. If the L1 cache can't find it, then we'll go through the normal translation of the virtual address to a physical address, and then use the physical address to look up in an L2. So an L2 cache is bigger, holds more data. So now we can be able to look up for that physically indexed address. In the physically indexed, it's very unique on each address because each frame that we want is an individual. So we do not have collisions. So this is great when we are doing shared code and data. All we have to do is know that we are accessing that same library, and we do not have to reload the information because we'll have it in the L2 cache. So in the figure, we're going to have the virtually indexed cache as a small L1 cache, and the physically indexed will be the much larger L2 cache, and it will look something like that. Paging also allows us to do things with these shared pages. So how are we going to be able to store that information? Well, we can have a page table entry point to the same memory as another page table entry from another process. So consider two applications, A and B, and they're sharing some library. So it would look like this in P1's logical space. It would just say, we have A1, A2, and a shared library, 2 pages for the shared library, and then some data. So in our page table, we're going to point that page 2 is actually some physical frame, and page 3 is another physical frame. Now comes along process 2. And process 2 wants to use that same library code. Well, we can have the page table point to exactly those same frames. So in this case, library 1 page for P2 is pointing to the same frame as another process. And now we have 2 processes that are sharing that actual frame. We can also share code and data pages the same way. So we could just have the code being able to be shared between these processes. So in this case, say there was another process that had using A1 code, we could share that code or share the data. But whenever we're sharing data, we've got 2 or more processes that are pointing to that same data. We're going to need to make sure that we have some synchronization. So remember, we want to have code that is protected from multiple processes accessing it at the same time. So we want to be thread safe, and we want to be reentrant. And we also have to be process safe in this case. So 2 different processes trying to access things. This is also a way for handling what happens in a fork. So when we duplicate the application to create the second process, then we are just copying all of those things, and we can actually just copy that whole page table. Now, what is not copied? Well, we must now have its own individual stack, so we would take care of that, of only updating the frames that handled the stack. So right now we have two different processes, both accessing the same data. But if I write in process 2, if I write to the page 4, then I'm actually changing the values in process 2, but not for process 1. So as soon as I do that right, I need to go allocate another frame. So in this case, data 2. And then update the frame, the page table, to access that new frame. And now every future access will get the correct data that is specifically for process 2. The rest of the pages are still being shared. So if we have code that is not being modified, then we only have to have one copy of it in memory at any time. Welcome back to the University of Colorado at Boulder. We've been talking about memory management, and today we're going to talk a little bit more about paging, but thinking about how to do it with what's called virtual memory. Virtual memory is a way to think about a system to where memory is not absolute, but is virtual. Well, what does that mean? We have a lot of different applications that we want to run. We're trying to run as many applications as possible on a system, and we want to be able to do it as efficiently as possible. And so far, we've been talking about how to have all of a process in memory at one time, and then swapping all of that process out to allow another process. But that can be slow. Are there other ways that we could do it that are actually more efficient? Think about this. We have a logical address space, and we have a whole bunch of things in that address space. We have code, we have data, we have heap stack. So let's think about a process that's running. We'll probably have some code that's running, and we need that code to be in RAM, so we put it into RAM somewhere. And as long as we are running inside that code, that's the only page that we need. We also probably have some data. We probably also have a stack somewhere. And so all of these things need to be in RAM at the time. But we don't need all of the stack. We don't need all of the heap or all of the data or even all of the code. We just need these pieces. So how can we now make it so that we can access all of this data, but dynamically, only keeping the ones that we need in memory? So only when we demand that they be there do they need to be there. The rest of the time, we don't care if that code is actually in memory or not in memory. This also allows us to do something else. It allows us to have an address space that is very, very large and RAM that is smaller than that address space. Such as if we were a 64-bit machine, we do not have 16 terabytes in which to access. Yet our logical address space could be that big if we wanted it to be. We need a way to be able to map those things and run programs that have or need more memory than we physically have. How can we make that happen? Well, we can do what's called on-demand paging. One of the problems with the system that we said before is that page tables are very, very large and they consume a lot of the RAM. And it would be nice to be able to keep those smaller. One of the key observations we can make, which we just talked about, was the fact that all pages in a logical address space are not needed inside of memory at the same time. In the simplest case, we could think about a program running, and while the program counter is within a page, that's the only page of the code we need. We could leave all the other pages on disk. We never even had to load them, which would also make things faster. If we then were running our code and our code jumped out of the current page and that other page is needed, we could go retrieve that page from disk before executing. Now this would be slow because every time we switch pages we'd have to go and get a different one. So there's probably some ways that we can make this a little bit more efficient. So instead of keeping just one page at a time sitting in memory, we want to keep a whole subset in memory. So that means we're going to keep a subset of the pages that are in the logical address space in RAM. We'll only load the ones that we need. If we have some code that we never execute, and that was sitting in a page, we would never need to load that page. Essentially what we're doing is we want to use memory as a cache, and we'll keep the things that we most frequently or most recently have used. And that way, everything that we're probably going to need will be in memory when we need it. Only once in a while will we need to go out and load something. This is relying on what is called a program's behavior to exhibit locality of reference. What does that mean? It means when you write code, you usually write it so that everything that you're accessing will probably be relevant to the next thing you access, such as think about a program that just goes linearly. It executes one instruction, and then will do the next instruction right after it, and the next instruction after that. Even if we have a loop, more than likely we're going to loop between 1 or 2 pages worth of code. So that would be that we have locality to where we're running a long time with just those 2 pages. This locality of reference is saying that if we've referenced a page previously, it is more likely that we will reference that page again as opposed to another page. So here's what we can do. We can think about how this locality works. Normally, we're going to be looping through the same instructions, processing things, but every once in a while, we're going to branch. We're going to branch maybe to another section of the code. Or maybe we'll call a application, or not an application, a function in another part of the code. But then we're going to return back where we were. So this is showing that we're really going to just be in a set of code that we probably are running over and over. That's the pages that need to be in memory for us. We don't have to go each time we are trying to jump to a new page. We could have those pages sitting there. All right. That's great. But new pages we have to get from RAM to disk, from disk to RAM, but only when the page is needed. And we could do the entire process on demand, which means we start off with nothing in memory. And then as we need a page, we will load that page. So we have 0 pages in our page table, and then the first reference to get the first instruction is going to cause a page to be loaded. And then we will subsequently take all of the pages that need to be there and load them as needed. So here's a kind of a visual of how that works. We have 3 different pages, A, B, and C. And we have actually a page table for the logical addresses, and we'll see that we have A, B, C, and A and C are in memory. But B is not in memory. So how are we going to represent this in that page table? So here's what the page table looks like. We have page 0 and page 2 both have RAM addresses, frames, in which to access, but B does not. So what we really need is to add another bit. We want to add a bit that says this is a valid address or this is an invalid address. And that allows us to say, well, 1 is just not loaded yet. So now if we try to access some data, we have to look to see whether or not we have a valid page or not. If we have a valid page, we can go to that frame. If we don't have a valid page, then we're going to have to load that page. So what are some of the advantages of this? Well, virtual address space can now exceed the physical RAM because we could have a page table and most of it would say that it's an invalid addresses. We have no frames that have been loaded for it. Therefore, we could have more space in our virtual address space than we had in physical RAM. And that as long as we only load as much as the physical RAM we have with what we currently need, then we'll be able to run. So essentially now we have decoupled the virtual memory, the logical address space, from the physical memory. And this will allow us to run many more applications. we can now have just a few pages loaded for each of the processes. It allows us to then be able to decrease the amount of time it takes to swap it out. Before, when we were loading the whole program and we needed contiguous space to do it, if we couldn't find any space, we'd have to remove a whole process. Now all we need to do is remove enough frames to give us enough frames to load the new program. If there's less things to swap, the faster we're going to be. We can also have very large sparse address spaces. So in our case, we allocate large stacks and heaps, but we rarely use them all. We might have very, very large data. Say we might want to be able to handle 100,000 items, yet we're only using 100 items in the nominal case. This does not hurt us because we don't have to load all 100,000 items into memory. If we were to use all of that space, say we had a large recursion that was going very deep, we might use a lot of our stack. In which case, when we need it, we can allocate it and allocate a frame for it. If we need to swap some of it out, we can swap some out. Not a problem with this virtual memory method. There are some questions we need to still answer, such as, how is a needed page going to be loaded into memory? It's great we were saying, when we need it, we'll load it. But how do we know we need it? How many pages should be in memory? I've loaded one. How many more should I load? Should I load most of them if I can, or should I always limit it? And then what happens if I say there's some limit and we exceed that limit? How do I choose which of those pages I should swap out? Here's how a page fault works. This is when we go to access a logical address and that logical address is not in memory. So the MMU is going to see that page is not in memory because the invalid bit is set inside the page table. And this causes a page fault trap. So the kernel is going to get notified that we are trying to access a page that is not in our currently in memory. We're going to save the current state of that process and determine why we are getting this fault. We're going to jump to the page handler to handle a page fault. And the page fault handler is going to do this. If we're referencing a page that's not in our logical address space, then we're going to segfault, just like we were doing before. Otherwise, if it's a reference to a good address and it's not in RAM, which is why we got interrupted, then we're going to load that page. How are we going to load that page? Well, we're going to have to find a free frame somewhere in memory, and then we're going to schedule a disk read to bring in that OS page. Sorry, that process page. We're going to bring in the process page that we needed, but disk reads take a long time. So in the meantime, we've saved our state. We're going to jump off and run other applications, other processes. At some time in the future, the disk will interrupt, telling the CPU that it has read that desired page, and the OS will get called, and that desired page is now in the free frame. So we can now update the page table, set the valid bit for that page, and mark which frame it actually got placed into. Now that we have that information, we can swap back to this process at the instruction that caused that page fault. Whether it was referencing more code or referencing a piece of data that we needed to get to, doesn't really matter. We start it back up at that instruction and it's off and running again. So let's think about how this works, and we'll do it visually. We have a PC program counter, and it's currently in page C of the process in frame 1, and it needs to jump to something that's in page B. We're going to go try to access page B in the page table and we'll see that, whoops, not there. It's invalid. So we're going to go and trap into the OS and tell it that we're doing a page fault. It's going to call that page fault handler. That page fault handler is going to go out to disk and get page B for us. It found a frame 3 was empty, so it's going to put B there. Then we're going to update the table, and then we can start running again and do the jump into B. There's different places that we can get the data from the disk. We could get it from the file system, which means we have to look up the file, go out and get the data, and we'll see in future lectures on this course about how the file system is laid out and how we find different pieces within the file system, but it takes a little bit of a while to traverse and find information. We could also do it with SwapSpace or the backing store. We can place things in there that are managed by the OS, and then we know exactly where it is and we can get it quickly. So this is faster and it avoids all that overhead of looking up things in the file system. There's a couple different reasons we could have information in the SwapSpace. Could be that when we first started, we put the whole executable into SwapSpace. And that way, once it's there, we can manage it. This is nice because it allows us to create the executable laid out contiguously, and therefore we know exactly where things are and be able to get to those pages quickly. Essentially, the file system stores things to where we don't know where things are and we have to go look it up. So we'd have to seek to find that page in the file system, but if we've laid it all out in SwapSpace as linear, then we can jump to it quickly. We could also have pages swapped because as we are running, we run out of space in RAM. And if we run out of space in RAM, we need to write things out to disk somewhere to hold on to that information. So the next time they're needed, we can quickly get them from the backing store and bring them into the system. All of this sounds great, but what's the performance? When we had it all in memory, we never had to load anything. Now it's not in memory, which means we're going to slow things down when we want to try to do something using virtual memory. How does it affect the performance? Well, a disk read is about 10 milliseconds, but memory reads are about 10 nanoseconds. So disk reads are very, very slow. So what we want to do is we want to limit the number of disk reads that we have to do, which means we want to limit the number of page faults that occur, because a page fault will then cause us to go out and read memory. So how can we calculate what the average access time is? Well, we can use the probability of a page fault occurring. So access time is the amount of times that a page is in memory, in which case we can do it in 10 nanoseconds, and the probability that a page needs to be loaded. So in this case it says P is the probability of a page fault. If we have a page fault, it's going to take us 10 milliseconds. If we don't have a page fault, the 1 minus P, then it's only going to take us 10 nanoseconds. So if we think about page fault happening 1 in 1,000, then our access time is going to be dominated by the microseconds. If we want to keep the average down close, within 10% of just accessing memory, we'd have to make sure that our page fault rate is less than 10 to the minus 7. So very seldom do we want to have a page fault in order to keep the system looking like it's running all in memory all the time. Now there's different ways we can do that. If we have page faults all the time, maybe we can predict what it is that we are going to need next and make sure that we're already reading that data into memory and getting it there before we need it. If we can reduce the page faults, our performance goes up. But because, again, memory reads are very fast and disk reads are very slow.
University of Colorado at Boulder. We've been talking about virtual memory and paging, and now we're going to talk a little bit about page replacement policies. You remember we have data in RAM, we have the logical address space for a process, and we have that process's page table. And the page table is allowing us to map between the virtual address space, the logical address space, and the physical address space in RAM. And you can see right here we have 2 out of the 3 pages for the process actually loaded, and 1 is not in memory. So we have A and C in memory, but page B is not. Now, how can we access B if all the other frames are already used? If X, Y, and Z are already in memory, taking up all the other space, and we need to access B. How are we going to do that? There are no available frames. Well, we must decide which of the pages that are currently in RAM needs to be evicted so that we can make space for B to be able to be put into memory. And this is a policy. It's an algorithm. It decides how it should be done. There are a number of different page policies that we can use, but what it wants to do is to bring in more pages on demand, and we run out of those free frames. So we need to have that policy that tells us how do we pick which frame is going to be evicted. We need to select a victim that's not currently being used. If we tried to take one out that was being used, we'd have to immediately swap it back in. So we want to pick one that's the best one to be taken out. Then it's possible that that page, when it's in main memory, has been modified. And so we have to save the current values in that page now to the disk. We have to then update the disk to say that that page is now invalid, and we need to load the new page from disk into memory and update the page tables for that new page being in a physical frame. But you might notice that anytime we have a page fault, then we're going to end up with 2 disk operations, not just one. We have to write the current data to the disk, and then we have to bring off the disk into memory the new page. But this is a big performance hit. Remember that disk is very, very slow, and now not only do we need to do one disk operation to load, but we also need a second disk operation to write out the current data. So how could we maybe get rid of this? Well, let's think about what we're doing. So here's the visual of what we were just talking about. We're in the code in page C, and it says to jump to page B. But if we look, we see that everything is full. We see that page B is invalid. So we're going to go ahead and go to the jump table, trap into the kernel. The kernel is going to then say, well, we need to pick a page that's already in memory and get it out. So we're going to pick frame 3, and we're going to take the data that's in Z, we're going to write it to the disk. Then we can go ahead and grab the data from B and write it into that new frame and update the table. And then we can actually do the jump. How can we reduce the penalty of those 2 disk operations? Well, we can employ a dirty bit. That dirty bit is going to tell us whether or not we need to write that data back out. If we're in, say, code, in a code page, and we're going to we're going to evict a code page, then more than likely we have not modified that code page because it only had code in there. So we didn't need to write it out because we already had the code on the disk. So we can actually now use this bit to be set anytime we change that frame. So if we write to the frame, we will set the bit. If we have never written to that frame since we loaded it, then we know we can reload that same page again without having to write it out first. This will save us that one operation, and it will make it much, much faster. So this is going to give us that little bit extra performance with only having to have one bit per page. And this is how we can do it. We can actually add some status bits to our page table. So here we have our physical frame addresses, and we can actually say whether or not each of those pages that we have is whether it's valid or invalid, whether or not it's dirty, which means that we've modified it, or we could even add another bit that tells us whether or not we can write to that page. So we can say these pages are only read-only, such as maybe if we were doing some code. And we can store all these extra bits within this page table. So the valid invalid flag we would use for our memory protection of creating page faults when the logical page is not in the physical space. We can also see whether or not it's a real page of memory by looking up the address and seeing it's in the page table or isn't. We could also use the other bits such as reading and writing. And again, when it's set to read only and we try to write to it, then we would cause a fault and trap to the OS, and we would get something like a segmentation fault. We could also add a few more bits to this. We don't need to be limited here. We could also use something called a reference bit that says, I have used this page for a read or a write. So anytime we access a page, we can actually say that it has been accessed and keep that information. So just for a recap, virtual memory. We only want to keep a few pages of the process in memory, and we're going to leave the rest of it sitting on the disk because we only need that few to execute the current process. As that process needs more pages, we'll bring them in as we need them, but we'll only keep a few of the pages in there at once. And that was on-demand or demand paging. We only retrieve a page when we need it. If we never need that page, we will never load it into memory, thus saving those extra disk IOs. Whenever the page is not in memory and we need it, we're going to create a page fault, which is a trap into our kernel. The kernel is going to block until it can retrieve that page for the current process. And while it's doing that, it can actually run other processes while it's waiting for that disk I/O to complete. But there's a significant performance hit, a lot of extra work, overhead we need to do whenever a page fault occurs. So in order to keep us to where we are most of the time spending executing, accessing memory, as opposed to having a page fault, we want to make sure that the frequency of a page fault happens very, very seldom. When memory is full, we need a page replacement algorithm to be able to decide which of the pages needs to be evicted. And we're going to use the principle of locality to say we're going to assume that the pages that have been accessed before are probably the ones that are going to be accessed again. So the ones we have loaded are more likely to be accessed if they've been accessed recently. We can use a dirty bit to tell us whether or not it's a clean or dirty page. Dirty page meaning that we've made a modification to that page. If we have not modified it, then we don't need to write it back out to disk. So what are some of the page replacement policies that we could do? Well, there's FIFO, first in, first out. That allows us to say, if we loaded that memory a long time ago, then when we need to access a new page and memory is full, we'll take the one that has been around the longest because it's probably not needed anymore. We have OPT, which stands for optimum. And in this one, we're actually looking in the future, saying, if I knew the page access sequence, then I could determine which would be the best page to keep me from doing a page I/O, doing some disk I/O to swap in a page until I absolutely would need it. So I could say these other pages would be needed before this other one, so that the one that's needed furthest in the future I could swap out. We could also use LRU, which is least recently used. So we'd need to keep track of when we've accessed memory and then look at which page has not been accessed for the most amount of time and then use that one to be evicted. So how can we tell which of these algorithms is going to work well? We need to do an evaluation. So how can we do evaluations? Well, in this case, we have a few variables. We have the algorithm that we're using. We have a page reference string, and in that case, we know the sequence of pages that will be accessed by the process. And if we have that information, then we can evaluate the reference string on how many page faults it will cause using that algorithm. And this all depends on the number of frames of memory. If I run it with 3 frames, I'm going to have a different number of page faults than if I run it with 4 frames. We're going to say that the algorithm with the lowest number of page faults is the most desirable. In this case, we know that every time we do a page fault, it costs us a lot of time to go to the disk and get information. Therefore, if we can reduce those page faults, reduce that disk I/O, then the algorithm for which of the pages we picked would be a better algorithm. The FIFO page replacement algorithm. How does it work? Well, we're just going to create a FIFO of all the pages that we have in memory. And then we can keep track of which one was accessed most recently and which one was accessed furthest in the past. So in this case, if we have a reference string, the sequence of page numbers that are going to be accessed, then we know that page 7 will be accessed first, then page 0, then page 1, 2, 0 again, 3, etc. We can assume for this example that there are 3 frames of memory. Therefore, we're going to create a FIFO. And we're going to have a pointer into which was the last, most recently accessed, or the furthest in the past accessed. So the first one is we're going to have that sequence. The first thing we'd have is 7. So 7 would be in the queue. Then the next one we reference is going to be 0. So we add 0 into the next frame, the next empty frame. And then 1. So now we have 7, 0, and 1 in our 3 frames that are available to us. But now we need to access page 2, but all of memory's full. We need to decide which one we're going to replace. Well, the last one to be added was 1. The first one, the one that was added first, was 7. So first in, first out, 7 needs to be replaced. And we will replace 7 with that new page of 2. Now we need to access page 0, but page 0 is already in memory. So therefore, we don't need to do anything. But then we're going to need to access page 3. Well, what's been in memory the longest? Well, we just move our pointer in our FIFO queue, and it's going to be 3. So we're going to replace 3. It'd be 0. We're going to replace 0 with 3. And we just keep doing this for the whole sequence. And every time we have a page fault, so in this case we had a page fault for 7, for 0, for 1, for 2, but not for that second 0 because it was already in memory, and then for 3. So we had a total of 5 page faults with this algorithm over this short sequence. We could do that for a whole long sequence and calculate the number of page faults. FIFO is easy to understand and it's really easy to implement. Every time we have a page, we just say which page was the next one to be loaded, and we just have that circular buffer that we keep going through, the queue, that tells us which page was first loaded and which one wasn't been in there the longest. That's really what we wanted to know. But performance can be poor. Suppose that page 7 was used all the time, but say it was used on the 5th or 6th page that we referenced, then we would have popped it out immediately, and then we would have had to load it again right away. So that doesn't make a whole lot of sense. In the worst case, it could be that every time we unload a page, that's the next page that we needed. Because we weren't trying to look ahead, we were just saying, when did we load it? If we used it a whole bunch of times, if we did 77773, then 3 would replace some page, and then whatever would follow that next would eventually maybe displace 7 when we need 7 again. So again, it's possible to come up with a sequence to every time we unload or we evict a page, that's the next page that we actually needed. So ideally what we want to do is we want to keep around the pages that we're going to use next and get rid of the ones we're not going to use until further in the future. And that's what the OPT algorithm does. So in OPT, stands for optimal, we want to replace the page that will not be referenced for the longest amount of time. Because we can guarantee that that will give us the lowest page fault rate. Meaning that we can show that if we tried to replace any other page, it would result in just as many or more page faults than always picking the one that's going to be used in the furthest in the future. Well, that's the problem. It requires future knowledge. Here's an example. So here's a sequence, a little bit longer, and we show what's going to happen in the future. And again, the first part of it is we still have a queue. Now we don't have to do first in, first out anymore, so we're not going to keep a pointer to it. So we're just going to have what is in each frame. And for the first 3, we have page faults. It's picking an empty frame to put in that new page. Then we get to the 2, and 2 is not in memory, causes a page fault. We need to now decide on which page is going to be evicted. Well, we're going to look in the future. We have 7, 0, and 1. And we're going to look in the future and see which one is used most distantly into the future. And we can see 0 is used almost immediately, so we don't want to get rid of 0. Then we're going to see that 3, 0 again, eventually 2, and then 1. So then 1's going to be used. So 0 is going to be used first in the future, then 1, and then 7. So again, in this example, 7 will be replaced with that page we wanted to add. So we evict 7 and add in page 2. Now we need to do page 0. Well, no page fault there, so now we need to go to the 3. And the 3, we need to access the page that's going to be used most distantly in the future. And again, we had 2, 0, and 1. 0 is going to be used first, then 2, then 1. So 1 gets replaced because 1 was used most distantly in the future out of the 3 pages that were in memory. So that's optimal, but we can't quite do optimal because we don't know what the future holds. So we're going to use something called LRU. If we look at how LRU runs, it actually looks at the past to predict what's going to happen in the future. So instead of trying to say what is going to happen in the future, let's look and see how often things were used in the past. And if it wasn't accessed recently, then it's likely it's not going to be accessed in the future. Therefore, we can select the victim that was least recently used. If we've been using pages, we want to keep them in memory. And if we have not used them in a while, those are the ones that we're going to go ahead and evict. It's an approximation of the optimal algorithm, which means we're not as good as optimal, but we're better than FIFO. So the page fault rate, the number of times the page fault occurs, is greater than optimal, but the page fault rate is much less for LRU than it is for FIFO. Here's an example. So again, we have our queue, we have our data, and now we're going to go to load page 2. And we have to say, well, which one was used most distantly in the past? Well, in this case, again, we look back. We have 0, 1, and 7. We can see 1 was used most recently, then 0, then 7. 7 was used least recently. Therefore, we're going to go ahead and replace 7 with page 2. Then 0 is still in memory, so the next time we have a page fault is going to be at 3. And now we're going to look in the past. Out of the pages that are in memory, 2, 0, and 1, which one was used least recently? Well, we can see 0 was used, then 2 was used, then 1 was used. So 1 was used least recently. So we're going to go ahead and say we can replace the 1, the frame that has 1, with the page 3. And we could keep doing that for more every single page fault. So when we go to load page 4, it's not in memory. So we need to decide which of those 3 frames, 2, 0, or 1, was used least recently. We can see 0 was used, then 3 was used, 2 wasn't used for a while. So now we'll go ahead and replace page 2 with 4. Now you can see page 0 never got unloaded. And it's because page 0 was used quite often. Every once in a while, we were accessing page 0. That tells us that page 0 should stay in memory because we were most likely in the future be accessing page 0 again. So this allows us to reduce that number of page faults. How can we implement this? Very easy. We keep a history of all the past pages that we have accessed. That could be that we have a whole bunch of pages that are loaded into memory. We remember when each one was last accessed and keep them in order. Except that's a lot of information. So we could just keep a sliding window. Tells us in the last so many accesses, here's the ones we were accessing. Anybody else, any of the other pages would be up for being evicted. But both of these are complicated and slow. So there's a number of different variations that are popular, such as using timers. We could, every time we access a page, just put the current time in there. So we timestamp it when it was used. Now all we have to do is find the one that has the smallest time. Problem is every time we want to get the timestamp, we're going to have to get the system clock. We're going to have to move those bytes around and do some things. And then we have to search for the page with the oldest timestamp. Again, not instantaneous. Takes a little bit of time. adds more overhead. We could do it with counters. Every time we access a page, we could do it with a incrementing a count. This is kind of like doing a timestamp, because the more often we access a page, the more often the counter will be incremented. But now we have to increment the page's counter every time we access it. So that slows down memory a little bit. We could start with the counter 0, and every time we reference it, we could set it back to 0. We could use the timer to then increment it. Problem is, all of these are a little bit expensive. We've got to update page counters on each reference. We must search the list again. How about if we store it as a linked list? Whenever a page is referenced, we put it on the end of the list. But we need to remove it from the middle of the list so that we can then place it on the other part of the list. If we were doing this as a linked list, then it means we've got to manage it and we have to search. Again, not the best thing. And if we try to do it with a stack data structure, we're going to end up with the same problem. So what we need is a fast way to be able to implement an LRU without actually having to mark and remember things. So there are some LRU approximation algorithms. We can add an extra bit called a reference bit that we will set anytime the page is referenced. So all we need to know is that when we go and look that page up, we're going to then say, all right, we've referenced that page. Therefore, the OS can look and see when a page was referenced. And then every once in a while, we can reset that reference so that we see what's happened in the near past. And this is a way to approximate LRU. There's three types of algorithms that use this reference bit, and we'll talk a little bit about them. There's one that uses additional reference bits. There's another one that does second chance, and another one that does an enhanced version of that. So additional reference bits. What we're going to do is, instead of having just a single reference bit, we're going to do reference bits, 8 different reference bits. So when we first create it, we're going to have the page table. It's going to tell us for each page, we're going to have a number of bits. Every time we access the page, we will set that top bit, that first bit. Periodically, what we want to do is we want to shift that information down. So we're going to move them all to the right. Move all those bits that were in the first bit, we're going to move to the second bit. And if they were in the second bit, to the third bit, etc. So it's going to shift down every time this timer goes off. What that allows us to do now is to have some history about what has happened, not just in the last time period, but in each of those 8 different time periods. As we reference bits again in our we'll set that top bit. So now we have 2 bits of information. And then we can use that information now to compare times. Because if we look, page 0 and page 1 have been referenced in the most recent time. And then page 0 was referenced again in the history, the second bit, whereas page 1 was not. So page 0 has been referenced more recently than page 1. And then both of those pages have been referenced more recently than page 2. We can use that information now to just build in some binary numbers. So if we do the first one, we'd have 1, 1, 0, 0, 0, etc. So anytime we don't have a bit set, you can assume it's a 0. And if we took 2 numbers such as 1, 1, 0, 0, 0, 1, 0, 0, or 0, 1, 1, 1, 0, 1, 1, 1, we know that that first one is greater than the second one. because the value is greater and we're always setting the top bit, which means if the top bit is set, it was more recently referenced than if the top bit was not set. So this makes it really easy for us to compare. All we have to do is find the value with the smallest value for these bits, and that would then be the page with the least recently used. This is easy to implement, a little bit of hardware addition. There's also one called the second chance algorithm. And in this case, we just use one reference bit that tells us when we last referenced this, and we keep a circular buffer. We keep a pointer into the next one to check, and this is the algorithm that we use. So if we need to evict a page, we're going to go through and look at what this reference bit says. And if it's been referenced, it will be set to 1. If it hasn't been referenced since we were last looked at the value, it would be set to 0. If the value has a 0, then that's the page we're going to replace. If the value has been accessed recently, the value will be 1, and what we're going to do then is set the value to 0 and move forward to the next item. So in this case, we can see in A, we're pointing to a victim that has a 1 in its reference bit. We're going to go ahead and set that reference bit to 0, move the pointer down to the next one below, but it also has a 1. We're going to set it to 0, and then we get down and we can see, if we look in column B, we get down to one that already had a 0. Therefore, that one has not been referenced since we last looked at it, the last time we'd been here at this referencing at this place within the queue. Therefore, we know that it hasn't been referenced in a while, and we will go ahead and replace that one. This has advantages. It's simple to implement. We have one pointer, a clock hand that's just running through our circular buffer, and we have to have just that one reference bit. And the circular buffer itself is just our page table, so all we really need to remember is where in the page table we last were looking, so we can look at that point again. Very fast to check a single reference bit and to set it. So it's usually pretty fast to find a page that has a 0 reference bit, but it only approximates LRU, and so there's going to be one disadvantage. In the worst case, so approximating the LRU is a good thing, an advantage. The disadvantage is it may be that everything got referenced and I have to go through the whole buffer looking at every single page that's in memory, setting a reference bit of 1 to 0, and then going through the whole buffer before I find one that has a 0. Could take a little bit of time if we have a lot of pages in memory. There are some other ones that allow us to count the number of times the page has been accessed. So this is one that really says, well, we want to replace the page with the lowest count. This is called least frequently used. There's another one called most frequently used that assumes that the smallest counts should be replaced, because the smallest counts, the most frequently used says we should replace the ones with the highest counts, because the ones with the smallest counts have just been loaded and will more than likely be used again. So what if a page was heavily used in the beginning but not recently? For either one of these, we need a way to maybe age the counts, which is kind of what we were doing with the reference bits. We were aging that information. Eventually, the history would be rotated off. But we could, in the count ones, be able to do this. But these methods aren't used very commonly, and their performance is not as good as some of the other ones. But originally, we were looking for an approximation to OPT. And we were using LRU as an approximation to OPT, and now we're doing an approximation of LRU. So we're getting a little bit further away. But in these approximations, we're using the past to approximate the future. What if we were smarter about looking at the past and we found things, not just a sequence, but a pattern? If we could see the pattern of what was being used, then we could be smarter about which pages we think will be accessed in the future. And this is going to be a better approximation of the page use than using some of these other algorithms. We can take advantage of locality on the fact that we think that if we've accessed this page, we know that we're going to probably re-access these pages again. But which one is most likely to be re-accessed? We could create working sets. The set of pages that we're working on now. Think about how your program works. We might have a long program, and in the beginning we're doing some processing and setting things up. The second part we're doing some manipulation, and the third part maybe we're doing some more code that's writing the data back out. In which case, in each one of those sections, the pages that we're accessing are going to be slightly different. And what if we could keep track of what the application was actually doing? We'll talk more about that in future lectures.